Greetings and welcome to this installment of Material Science Problems. And this one is about diffusion in a pure metal. The question we have gives us the pre-exponential and the activation energy for the diffusion of iron in cobalt. So let's just write down what we've got and then we'll see where we're going with this. So the pre-exponential is given as 1.1 times 10 to the negative fifth meters squared per second. And our activation energy, QD, is 253.3 kilojoules per mole. And we know that we've got iron going into cobalt. And the question asks at what temperature, so we need to find some temperature at which our diffusion coefficient is equal to 2.1 times 10 to the negative 14th meters squared per second. Again, we're looking for this temperature at which this happens. Well, I'm going to use our diffusion equation, which is d over our pre-exponential equal to e to the negative qd over rt. Understanding our exponent laws, this negative simply means the inverse of this entire term here. So I can take the inverse of both sides, so this also works. Pre-exponential over the diffusion coefficient equals e to the qd over rt. Now I can use either of these. We can rearrange things as needed. Well, this is pretty much a plug and chug where we have d naught right up here, our diffusion coefficient here, E is of course a constant, QD is given right there, R is the gas constant, so make sure we know that. R here is the gas constant. And that is 8.314 joules per mole Kelvin. All right, so we'll just do all this in variables and start with this one right here. So I'll just rewrite that. E to the QD over RT. And I'll take the natural log of both sides. Now, taking the natural log of e to some exponent, you end up just with the exponent. So take the natural log of d naught over d And the natural log of e to the qd over rt is simply qd over rt. Now I'm going to take both sides here and multiply by t. So on this side I get t times the natural log d naught over d equals, well, my t's cancel out here and here, so I should have qd over r. So to get t by itself, I'm going to divide through by the natural log of d naught over d. And I'm almost done. I have my expression for the temperature. So the temperature equals qd over r times the natural log of d naught over d. And I'm going to plug my numbers in here. So I've got 253.3 kilojoules per mole, all divided by 8.314 joules per mole Kelvin times the natural log of 1.1 times 10 to the negative fifth meters squared per second, all over 2.1 times 10 to the negative 19th meters squared per second. And let's take care of some of our units here. Meters squared per second over meters squared per second cancel out. My moles cancel out, per mole and per mole, top and bottom. But watch out for this. It's a kilojoule. I can only cancel out the joule, so I have to take that and multiply by 1,000. And then I can get rid of that kilo. And all that's left is per Kelvin, and that's on the bottom, so that comes up on top. So on the top we have 253,300 all divided by 8.314 per Kelvin times, and evaluating natural log of 1.1 times 10 to the negative fifth over 2.1 times 10 to the negative 19th, you get 20.077 and no units. And then making all that work out to 1518 Kelvin, which equals 1245 degrees Celsius. So this was a basic problem about diffusion in a pure metal of iron into cobalt. The key equation was the diffusion equation here, and we were just given several of the parameters, plugged them in after solving for our temperature, and we were able to find the temperature at which this setup has a diffusion coefficient of 2.1 times 10 to the negative 19th meters squared per second.